Good morning, all of you. In this session, I am going to explain about design of split muff coupling. Okay. In this session, I will explain how to design a split muff coupling. These are the important conversions. 1 Pascal equal to 1 Newton per meter square. 1 megapascal equal to 10 power 6 Newton per meter square. 1 megapascal also is equal to 1 Newton per mm square. Okay. 1 gigapascal equal to 10 power 9 Newton per meter square. 1 giga equal to 10 power 9. 1 Pascal equal to Newton per meter square. Okay. That value also equal to 10 power 3 Newton per mm square. Okay. Now, in yesterday class, already we discussed about all these formulas. Okay, power P equal to torque into angular velocity. Okay, from this equation, we can get the value of torque T. Okay, torque T equal to 60 into P by 2 pi n. Omega equal to 2 pi n by 60. Okay, so this is the formula for torque. Torque for solid shaft. This is the formula for torque for hollow shaft. Okay. So these two formulas are very important for design of solid and hollow shafts. Okay. These are the important design formulas for key for a sunk case. For design of sunk case, we are using these formulas. Power transmitted by, already we know the power transmitted by the shaft, power P equal to T into omega. Okay, from this equation, the mean torque T equal to 60 into P by 2 pi n. Okay. So this is the formula for torque transmitted by the solid shaft. Torque equal to pi d cube by 16 into tau. Okay. From this equation, you can get the value of the diameter of the shaft. Okay. Now this is the formula for torque transmitted by the key. Okay. F is the tangential force acting on the key. D by 2 is the radius of the shaft. Now L is the length of the key. Okay. The length of the key always depends upon the hub. Okay. Now the width of the key equal to W, W equal to D by 4, thickness of the key T equal to D by 6. For verification, for checking the strength of the key, we are using this formula torque T equal to L into omega, L into W into tau into D by 2. L is the length of the key, W is the width of the key, tau is the shear stress, D by 2 is the radius of the shaft. From this equation, you can get the value of tau. Okay. Now, in this case, you can get the value of shear stress induced in the key material. Okay, torque transmitted by the key equal to length of the key into thickness of the key by 2 into crushing stress induced in the key into radius of the shaft. Okay. So these all are the important formulas for design of shaft and keys. In this session, I am going to explain about design of clamp coupling. Clamp coupling, also known as compression coupling or split muff coupling. Okay, clamp or compression coupling or split muff coupling. Okay, so this is the diagram for split muff coupling. So this is the animated view of a split muff coupling. In this coupling, the muff or sleeve is made into two halves and are bolted together as shown here. The halves of the muff are made of cast iron. That means the material used for coupling is cast iron. The shaft ends are made to butt each other, and a single key is fitted directly in the keyways of both the shafts. One half of the muff is fixed from below, and other half is placed from above. Both the halves are held together by means of mild steel studs or bolts and nuts. The number of bolts may be 2, 4, or 6. The nuts are recessed into the bodies of the muff muff castings. This coupling may be used for heavy duty and moderate speeds. The advantage of this muff coupling is split muff coupling is that the position of the shafts need not be changed for assembling or disassembling of the parts. Okay, here you can observe this is a split muff coupling. Okay, this is a shaft. Okay, this is a key. These are the nuts and bolts. Now you can observe the video of a split muff coupling. So this is a key. This one is a split muff. These are the nuts. This one and this one is the shaft. Okay, these are the bolts. Here couplings are used to join two shafts. Okay, so these two hubs are the split muffs, and this one is the key. These are the bolts, hexagonal bolts, and these are the hexagonal nuts. Okay. Now this is the cross-sectional view of a split muff coupling. This is the front view and this one is the side view. Okay. Now I am going to explain a design procedure of a split muff coupling or clamp or compression coupling. Okay. In first step, you have to design a solid shaft. Okay. In first step, you have to design a suitable diameter of a solid shaft to transmit the required power from one shaft to another shaft. Already we know that power P equal to torque into angular velocity. Already we know that angular velocity omega equal to 2 pi n by 60. Torque from this equation, the mean torque transmitted by the solid shaft torque T equal to mean torque T equal to 60 into P by 2 pi n. Okay. From this equation, you can get the value of torque T. After getting the torque T, you have to substitute this torque value in this equation. This is the formula for torque transmitted by the solid shaft. Torque T equal to pi d cube by 16 into tau. D is the diameter of the solid shaft. Tau is the shear stress induced in the shaft material. Okay. From this equation, you can get the value of diameter of the solid shaft. Okay. So here in first step, we can design the suitable size of the solid shaft. Okay. By using these steps, you can design a solid shaft. In second step, you have to design a suitable size of a key. Here, width of the key W equal to D by 4 and thickness of the key equal to D by 6. And the length of the key in each shaft, equal to half of the length of the sleeve. Here, the length of the sleeve L equal to 3.5 D. Okay. L equal to 3.5 D is the length of the sleeve. You have to consider half of the length of the sleeve. Okay. So the length of the key in each shaft equal to half of the length of the sleeve. 3.5 D by 2. Okay. Here, this formula is used for design of key on the basis of shearing strength. Here you have to substitute the value of mean torque, length of the key, width of the key, and radius of the shaft. From this equation, you can get the value of shear stress induced in the key material. Okay. In second case, you can get the value of crushing stress or compressive stress induced in the key material. Okay. From this equation, you can get the value of sigma c. Okay. In third step, you have to design a suitable size of sleeve or muff coupling. Here, tau c. Here, the material used for coupling material is cast iron. So, tau c is the permissible shear stress induced in the cast iron material. And capital D. Capital D is the outer diameter of the muff or sleeve. Capital D equal to 2D plus 13 mm. And small d is the inner diameter of the sleeve or muff coupling. Okay. Now this is the formula for torque transmitted by the hollow shaft. Okay. Now here you can observe this sleeve or muff coupling is a hollow shaft. So you have to design a sleeve or muff coupling as a hollow pipe. So you have to consider this formula for torque transmitted by the hollow shaft. Torque equal to pi by 16 into tau c into d cube into 1 minus k power 4. Capital D equal to 2d plus 13 mm and small k equal to small d by capital D. Small d is the diameter of the solid shaft. Capital D is the diameter of a outer diameter of a sleeve or muff coupling. Okay. From this equation, you can get the value of tau c. Okay. In step number 4, you have to design a clamping bolts. Okay. In step number 4, you have to design a suitable size of bolts and nuts. Okay. For that purpose, you have to use this formula for design of bolts and nuts. Here, T is the torque transmitted by the shaft, and mu is the coefficient of friction between the two mating parts. Okay, mu is the coefficient of friction between the two moving parts. That means coefficient of friction between two halves of the muff or sleeve. dB is the core diameter of the bolt. dB is the core diameter of the bolt. Sigma T is the tensile stress induced in the bolt material. N is the number of bolts. D is the diameter of the shaft. Okay. From this equation, you can get the value of required size of a bolt, core diameter of a bolt. Okay. N equal number of bolts, small d equal diameter of shaft, sigma T equal to tensile stress induced in the bolt material. Okay. Coefficient of friction between the muff and sleeve, muff and shaft surface equal to mu. Okay. So these are the 4 steps used for design of clamp or split muff coupling. Okay. Now this is the question. Design and make a neat dimension sketch of a split muff coupling or clamp or compression coupling, which is used to connect two steel shafts transmitting 40 kilowatts at 350 RPM. The material for the shafts and key is plain carbon steel, for which allowable shear and crushing stresses may be taken as 40 megapascal and 80 megapascal respectively. And the number of bolts connecting the two halves are 4. The permissible tensile stress for bolts is 70 megapascal. The material for the muff is cast iron, for which the allowable shear stress may be assumed as 10 megapascal. The coefficient of friction between the muff and the shaft surface may be taken as 0.3. Okay. So this is the split muff coupling. Okay. This, from first of all, you have to identify the given values from given question. Okay. In this question, first of all, you have to observe the given values. Here you have to design a split muff coupling. Okay. Split muff coupling or clamp coupling or compression coupling. Okay. Here the power transmitted by the shaft is 40 kilowatts. Okay. Here the power transmitted by the shaft is 40 kilowatts. That means 40,000 watts. and the speed of the shaft is 350 rpm. Okay, the speed of the shaft is 350 rpm. That means n equal to 350 rpm, and this one is p, power p. Okay, power p equal to 40 kilowatts. Okay, here the material used for shaft and key is carbon steel. That means the material used for shafts and key both are same. Here the allowable shear and crushing stresses. Here shear stress for key and shaft material is 40 megapascal. Okay, shear stress for shaft and key material is tau equal to 40 megapascal, and sigma c crushing stress equal to 80 megapascal. Here the number of bolts used for split muff coupling is 4. Number of bolts equal to n equal to 4. Okay, n equal to 4 bolts. Here the permissible tensile stress for bolt material, that is sigma t equal to 70 megapascal for bolts. Here the material used for coupling is cast iron, so the shear stress for cast iron material is 10 megapascal, and the coefficient of friction between the muff and the shaft surface is 0.3 mu. Okay, mu equal to 0.3. Okay, so these are the given values. Power P equal to 40 kilowatts. 1 kilo equal to 1000, so 40,000 watts. 1 watt equal Newton meter per second. Speed n equal to 350 rpm, and shear stress for shaft and key material is tau s equal to 40 megapascal. 1 megapascal equal to 1 Newton per mm square, and shear stress for sleeve or muff coupling is cast iron, that is tau c equal to 10 megapascal, 10 Newton per mm square, and the compressive stress induced in the key material is sigma c equal to 80 megapascal. Tensile stress for the bolts equal to sigma t equal to 70 megapascal. Okay, tensile stress induced in the bolt material sigma t equal to 70 megapascal. That value equal 70 equal to 70 megapascal equal 70 Newton per mm square. Okay, these all are the given values. Here in step 1, you have to design a suitable size of the solid shaft. Let small d is the diameter of the solid shaft. Already we know that formula, power transmitted by the solid shaft, power P equal to T into omega. Omega equal to 2 pi n by 60. So power P equal to T into 2 pi n by 60. That value from that equation, torque transmitted by the solid shaft, torque T equal to 60 into P by 2 pi n. Okay, this is the mean torque. So from this equation, you can get the value of mean torque T. Okay, already we know that power P equal to 40 kilowatts and n equal to 350 rpm. Okay, n equal to 350 rpm. After substituting value of power P and speed, you can get the value of torque T. Torque T equal to 1100 Newton meter. Okay, 1100 Newton meter. Already we know that the given power is in Newton meter per second. So the torque also in Newton meter. Okay. Now you have to convert this meter into mm. 1 meter equal 1000 mm. So the mean torque value is 11 lakhs Newton mm. Okay. Already we know the formula for torque transmitted by the solid shaft. Torque equal to pi d cube by 16 into tau. Already we know the value of tau, shear stress induced in the shaft material. So now you have to substitute the value of shear stress and torque T in this equation. From this equation, you can get the value of shaft, suitable size of the shaft, diameter. Okay, diameter of the solid shaft equal to 52 mm, but the standard size is 55 mm. Okay, so this is the required diameter of the required size of the shaft. Okay, 55 mm is the outer diameter of the solid shaft. In second step, you have to design a suitable size of key, sunk key. Tau s or tau k is the shear stress induced in the key material. Sigma c is the crushing stress induced in the key material. Here you can observe the crushing stress sigma c equal to 80 mm is 2 times the shear stress induced in the key material. So you have to use a square key. Okay, if the crushing stress is 2 times the shear stress, then you have to use square key. Okay, that means width of the key equal to thickness of the key. Already we know that width of the key equal to d by 4. Okay, d by 4 is the width of the key. Here for square key, width equal to thickness, so thickness also d by 4. Okay, for a square key, width equal to thickness, so thickness of the key equal to d by 4. Now the length of key in each shaft equal to half of the length of the sleeve. Okay, 3.5 into d is the length of the sleeve, so you have to consider half of the length of the sleeve. L equal to 3.5 d by 2 equal to 97 mm is the length of the key. Okay, these are the dimensions of the sunk key. Now you have to check these three values. Okay, now you have to consider the shearing strength of the key. This is the formula for torque transmitted by the key. Okay, torque T equal to length of the key into width of the key into shear stress induced in the key material into d by 2. Okay, now you have to substitute the value of torque transmitted by the solid shaft, and length L equal to 97 mm, width equal to 14 mm, d by 2, d equal to diameter of the solid shaft 55 mm. Okay, after substituting these values, you can get the value of shear stress induced in the key material. Shear stress induced in the key material tau k equal to 29.4 Newton per mm square, but the given shear stress is 40 megapascal. Okay, this induced shear stress is less than the permissible shear stress, so the design of key is safe on the basis of shearing strength. In similar way, you have to consider crushing strength of the key. Okay, this is the formula for torque transmitted by the key. Torque T equal to L into T by 2 into sigma C into D by 2. L is the length of the key. L equal to 97. T is the thickness of the key. Thickness equal to 14 mm. 14 mm. So from this equation, you can get the value of crushing stress. Crushing stress equal to 58.9 Newton per mm square. Okay, 58.9 Newton per mm square is the induced crushing stress in the key material, but the given permissible stress is 80 megapascal. Okay, this induced crushing stress is always less than the given permissible stress. So the design of key on the basis of crushing strength also safe. Okay. So since the induced shear stress and crushing stresses are less than the permissible stresses, therefore the design of key is safe. Okay. In third step, you have to design a suitable size of sleeve or muff coupling. Okay. Already we know that this is a hollow pipe. Okay. Sleeve or let's consider the sleeve or muff coupling as a hollow pipe. Tau C. Here the material used for coupling is cast iron. So the shear stress induced in the cast iron material is tau C. Tau C equal to 10 megapascal. That value equal to 10 Newton per mm square. Now capital D is the outer diameter of the sleeve. Capital D equal to 2D plus 13 mm. That value equal to 123 mm. And here small d equal to diameter of the solid shaft. That value equal to 55 mm. From this equation, you can get the value of diameter ratio K. K equal to small d by capital D. Okay. Here small d equal to 55 mm. Capital D equal to 123 mm. Okay. So the diameter ratio K equal to 0.447. Okay. Now this is the formula for torque transmitted by the hollow shaft. Okay. So now you have to substitute the value of mean torque T and outer diameter and the diameter ratio value. You can get the value of tau C. Shear stress induced in the coupling material. Tau C equal to 3.135 Newton per mm square. But the given permissible stress is 10 megapascal. Okay. So since the induced shear stress in the muff coupling is less than the permissible shear stress of 10 megapascal, Therefore, the design of sleeve or muff coupling is safe. Okay. In given question, the cast iron, the permissible stress for cast iron is 10 megapascal. Here, 3.135 is the induced shear stress in the coupling material. So this induced shear stress is less than the permissible stress. Okay. So the design of sleeve or muff coupling is safe. Okay. In fourth step, you have to design a clamping bolts. Okay. Let db is the core diameter of the bolt, and n is the number of bolts. From given question, the number of bolts n equal to 4. Small d is the diameter of the solid shaft, d equal to 55 mm, and tensile stress induced in the bolt material sigma t equal to 70 megapascal. Okay, this one also given value. Now the coefficient of friction between the sleeve and shaft surface is mu equal to 0.3. Okay, these all are given values. Okay, let T is the torque transmitted by the solid shaft. Torque T equal to pi square by 16 into mu into dv square into sigma T into n into d. Here mu is the coefficient of friction between the sleeve and shaft surface. dv is the core diameter of the bolt. Sigma T is the tensile stress induced in the bolt material. N is the number of bolts. Small d is the diameter of the solid shaft. Now you have to substitute the value of T, mu, sigma T, N and D. Okay, after substituting these values, you can get the value of dB, diameter of the bolt, core diameter of the bolt. You can get the value of core diameter of the bolt, dB equal to 20 mm. Okay. So this is the final answer for this problem. Okay. For design of any coupling, first of all, you have to select a suitable size of solid shaft. After getting the size of a shaft, you have to design a sunk key. Okay. After that, you have to design a sleeve or muff coupling. Okay. In next class, I will explain how to design a flange coupling. Okay. In next class, I will explain how to design a protective type flange coupling and unprotective type flange coupling. Okay. This is very important problem for exam point of view. Okay. Exam point of view, it is very important. In next class, I will explain with example. So these all are steps for design of clamp or compression or split muff coupling. In first step, we have to design a suitable size of a solid shaft. Okay. Here we are using two formulas for design of solid shaft: torque power P equal T into omega and torque T equal pi dq by 16 into tau. Okay. In second step, you have to design a suitable size of a key. Okay. Width, thickness and length of the key. In third step, you have to design a sleeve or muff coupling. In fourth step, you have to design a suitable size of bolt. Okay.